UCLA, and she'll talk about optimal transport and the Stefan problem.
Hi, good morning, everyone. I actually don't see who introduced me, but thank you. Thanks for letting me speak for this problem, even though it's not directly relevant to the theme of the workshop, but hopefully this is a new connection that we discovered between the optimal transport, so to speak, and Stefan problem. So perhaps, hopefully that you find some new connections also and new ideas. Okay, so let me share my screen. Okay. Okay, so this work is joint work with Inwon Kim at UBC. And so Younghyun, if he was going to speak, then he will talk about more about the optimization problem. But my perspective is more about PDEs. So my focus is on PDEs. So I'll start from the Stefan problem. So what is Stefan problem? So there are two Stefan problems. First, I'll talk about the supercooled Stefan problem that we are going to focus in this talk. The second type of problem I will speak shortly in the next page. And that's what Alessio will focus on in the next talk. So the supercooled Stefan problem is about freezing, but not just normal water, it's supercooled water. So I don't know if you have seen on the YouTube TV that if you just Google supercooling, you pull out some water, supercooled water from the fridge, and you pour it, and you get very unstable and sudden growth of the ice that water is turning into. So that's supercooling. And while the physics of the supercooling is still quite not to be understood, but we have a PDE that models this phenomenon in principle, which can be written as follows. Sorry, what happened? So here the important thing is the minus sign there. So that will, so whether you have minus or plus here will decide whether your set here that you are looking at decreases in time or increases in time. So in this case, here the region where U is positive denotes the region where supercooled water sits. Okay, so when you turn on the time, some either due to some stimulus or something, the supercooling process starts, and then what was initially supercooled water will turn into ice. And the equation here that's given describes the dynamics of it. Okay, so it is about freezing of supercooled water, and because it is freezing problem, it is unstable. So what I mean is that as you expect from ice crystals, you expect fractals for interface. And it is known that sometimes if you solve for this equation, the freezing can all of a sudden produce a thick piece of ice, which means that you can jump. Oh, I think I shouldn't mess with my mouse. You could jump this continuously over time. So the solutions are irregular. There's in general no uniqueness, as you can see later. And yeah, so this problem has been studied a lot, both in PDE literature and also from probability literature. But there is no global existence in multi-dimensions. Well, so that's what we studied. There has been no result. Okay, so I hope one more comment is that this, if you look at this problem and do integration by parts, it will follow that the speed of freezing of the interface. So the speed of this interface that turns water to ice will be given as the gradient of U. So that's what this equation is describing. right? So inside you resolve heat equation on the interface, it describes how fast the interface moves. That's what the PDE is about. Okay. So in contrast, the Stefan problem that's more, that's better behaving is the problem of melting. So here, U is not the minus temperature of the supercooled water we talked about. It's the normal positive temperature of warm water. So warm water melts, and the procedure is supposed to be smooth, as you observe in any melted region of lake or something like this, right? So a simple way to describe the difference from the freezing problem with melting problem is the following, that if you look at this function, it's an increasing function of U. So in this way, you can vision this equation as a parabolic equation. Whereas before you cannot, this is not true, your function is not increasing. So that is not a parabolic equation, whereas this one. So this one is stable and features regular free boundary, well-posed, have unique solutions for given initial data. And of course, there's many open questions for the regularity of the Stefan problem, because still there can be singularities due to topology changes and so on. And this is what Alessio will present, I believe, in the next talk. All right. So we're going to mainly talk about the supercooled Stefan problem, because we are talking about well-posedness of this problem in multi-dimensions, which is very well known for the melting problem. So it's more exciting to talk about the freezing problem. We are going to study this in the optimization with optimization structure, but let me explain how we come around this. So because it's about water freezing into ice, it's very natural to consider the solutions given by interacting particle system, right? So you think about a heat particle starting from somewhere, and then you travel, where did it go? You travel from a fixed point, you're a Brownian motion, okay? You are a heat particle, so you move like Brownian motion, and then you hit this interface where ice is, and then you turn yourself into ice. So that is the way to think about this problem, by a particle motion. So for one dimension, people use this approach to prove well-posedness of the problem. So I listed a few references. So all of these references deal with 1D system. But for multi-D, if you try this approach, and people have tried and obtained partial results, you see that compactness is a big issue. And it's not even known if this particle system, which has randomness in it, has a deterministic continuous limit. Okay, so instead, our approach, we still will look at Brownian particles, but with some optimization structure, and this is, this is what we tried that's new, and this turns out to be successful. So you will see that we obtain well-posedness results for the multi-dimensional supercooling Stefan problem. Okay, so that's what we wanted to present, what I wanted to present. So first, let's start with a stopping time. I confess that I do not know much probability, so this will be just as much as I know and how I understand it. But my co-author can, of course, answer more advanced questions. So a stopping time of Brownian motion is just a random time prescribed to satisfy the Markov property, right? So if you are at given time t, and how you decide to evolve, whether stop or not, only depend on the information given before time t. So an easy example also how we will think about this is given by heating time. So if you have a set in space, S here that I draw with a blue color, right? So S is a set in the entire space Rn with whose complement is this round set here, then you can think about Brownian particles starting inside in this empty space, and you just travel. And the first time you enter this set S, you stop there. And that's an example of a stopping time. And if the set S is nice, of course, all the stopped particles will be concentrated on the boundary of this set S. Otherwise, it's not so clear if S is just, for instance, only measurable. Okay. So our problem is based on the Skorokhod problem, which is a very popular problem, it seems, in math finance literature and also in probability literature. So the problem is as follows. For two bounded compactly supported, so that may be just technical. So two probability measures, mu and nu, we consider a stopping time that connects these two probability measures such that, right, I mean, so this, how are they related? You start from distribution mu, right? So you start a Brownian motion with the initial distribution mu, and then they travel. And then by a stopping time, they stop. And if you collect all the stopped particles and take their distributions, it's nu, okay? And the stopping time has a constraint. You must satisfy that the expectation of this stopping time is finite, which means that you cannot forever sit and wait for this stopping time to occur. Because if you allow that, all kinds of measures can be achieved by this way. So you want to limit in a certain way how the stopping time operates. So this is a classical problem in probability, and it's known that such stopping time exists for given mu and nu, if and only if the following works. So this order works. The inverse of the negative Laplacian is ordered, which means, what it means is that the target measure nu, which you want to achieve at the end of the stopping times, is more spread out than mu. And that's natural because you have to start from mu and somehow have to spread out by Brownian motion and achieve nu. Okay. So that is the called Skorokhod problem. It's talking about Brownian, so two probability measures, mu and nu. Okay. So now there is an optimal Skorokhod problem. Okay. So again, for fixed Brownian motion, mu and nu, you consider all types of stopping problem with finite expectation that minimizes this cost. So here is your optimization structure. So your cost depends on the stopping time, and it's given by expectation of this integral where you have this Lagrangian that has monotonicity property. Okay. So if you do not care about how it transfers from mu to nu, it is closer to the optimal transport, right? The classical optimal transport we know. But now we care about how actually these stopping times occur. And okay. So this is somewhat closer to control problem, actually, except that you are not looking at a fixed final time, big T. You are looking at, you can stop at random times by stopping time rule, and you want to optimize. So in relation to what Taipung talked about on Monday afternoon, we are looking at this vanishing particles, right? I mean, we are interested in vanishing particles and actually how they disappear. And the law here is by stopping time. Okay, and the cost cares about that. Okay, so in this case, what's interesting is that the optimal stopping time actually is given by heating time. Okay, so here is a hint of free boundary problem for you, right? So if you optimize this cost over all stopping times that starts from mu and ends as nu, then you get a heating time of a barrier set. Okay, so that is the barrier I drew below, the set S. And you can see the red particle that starts from initial distribution mu. You travel, you hit this set, which is a space-time set. And then when you reach the boundary of S, you stop. Or when you first enter the set, you stop. Okay, so that it's known that it's given by the heating time. Okay. Moreover, the optimal stopping time and the barrier is unique. So in 1D, these references, there are much more, but I only give a few that that's representative of the work. So in 1D, there's McConnell, Cox, Wang, and also there's many others. And the point of view that connects this problem to optimal transport, even though mostly in 1D, is given by Begelbach, Cox, and Husman. And the PDE approach is first given by Gusap and Inwon Kim and Aaron Tama. Okay, so where am I going? I first talked about the Stefan problem, and then I talk about this optimization problem. So we'll see that there is a connection. Okay. So before I talk about this, let's say one more thing. So if this Lagrangian is strictly increasing in time, then the barriers are given by the picture on the right. Okay, so it is a barrier that increases over time. So the picture looks like this, right? That's on the right-hand side. And well, that's natural because if L, the cost, is increasing over time, then it's better for you to move a lot when the time is at earlier times, right? So it makes sense that your barrier increases over time. On the other hand, if the cost decreases in time, then the barrier opens up more over time, and you have the picture that corresponds to the left-hand side of the, okay. So the vertical axis is always time for me. So again, what happens is that these red particles move, and then they stop at a point. And then you project it you project it to the x-axis, and then you look at the distribution of the stopped particles, and then that will become your target measure nu. Okay, please ask me if this is not. You have a question about the formulation of the problem.
So maybe can you repeat what is L?
L is, just a second. L is this Lagrangian here in the cost, right? So the cost depends on the stopping time, right? So it ranges, it counts the Lagrangian, right? That is related to the Brownian motion BT as it moves, right? Until it stops. And you take, expectation, so you take the integral over the space.
Okay, thank you.
Okay, good. Anyone else? Okay, so we are talking about optimal Skorokhod problem for fixed probability measure, mu and nu, so far. And yeah, depending on the monotonicity, you have two different pictures. Okay, so this is the question. For given mu, tau, and nu, there is a barrier set, right? So tau is the optimal stopping time. So it's really for given mu and nu, there is a barrier set, right? Associated with the optimal stopping time. Now, can we understand that as a free boundary problem that depends on mu and nu? That is the question. And okay, so we'll answer this question. So to study, right? I mean, so far, let me just explain that the point of view using Brownian motion and stopping time and the Lagrangian and so on is Lagrangian. Yeah, so you look at each particular path and you care about cost depending on those paths and so on. But if you want to understand this as a PDE problem, of course, the natural approach is to think about Eulerian variables associated to it. So we change from Lagrangian to Eulerian. So that is not our work. This was previously done by Gusup and Inwon Kim and Palmer. So you can represent it by PDEs in this way. It's kind of interesting that I never thought that a heat equation with a sink term, or a heat equation with a sink term would actually generate the interface. But of course, it depends on the regularity of the sink term. So here, eta represents the active Brownian particles, right? So eta is the active, the distribution of active Brownian particles at a given time. And it keeps losing particles, of course, as you go because of the stopping time. So what you have lost here is given as rho. So rho represents the stopped particles. So the first equation is a simple heat equation with a sink, right? And the conditions are that this set S barrier, right? The conditions is that rho is concentrated in the set S and eta has nothing in S, right? So the active region for eta would be the complement of S. And of course, if you collect all the stopped particles, then you should get nu. So, and of course, initially you should be all active. So eta is at time 0 is equal to mu. Okay, so that is the Eulerian formulation. Okay. So now let's see. I mean, if I can somehow figure out what this rho is in terms of eta, then I am very close to the PDE formulation of the problem, right? So far, rho is mysterious. Okay, so can we figure that out? And yeah, at least formally. So the barrier is a set of the form T equals S of X, right? The boundary of, sorry, not the barrier. The boundary of the barrier is formally when the barrier is very nice, which will not be the case, but suppose it's very nice. It's actually, you know, you expect fractals, right? But suppose it's nice, and then the boundary is given by Sx equals T. And so, you know, that's represented like that. And if, you know, everything is nice and good, then you expect that rho is exactly the target measure concentrated on this graph, Sx equals T. Right? Because when it stops, it becomes part of the target measure distribution. So, okay, so if you, I mean, this is of course not Dirac delta, this is the surface measure, now this expression equals, right, nu, right, so maybe now I don't know. So here in the last line, if you observe that this is true, right? Why? Because the set where eta is bigger than 0 is exactly the complement of S. So if you take the derivative, depending on the monotonicity of your barrier set, you either get plus sign or minus sign. Okay, so in this case, because as the active region is decreasing over time, you get the minus, so that the surface measure delta equal to the minus time derivative of the active region characteristic function of the active region. So so now I can formally expect this equation. Let's see what happened. Yeah, this equation, right? So I just plugged in. What happened is that instead of minus rho, I plugged in plus this term, the time derivative term. And this is exactly the supercooled Stefan problem, except that there is a weight nu, okay, in front of the time derivative of the set term, the characteristic function. Okay, similarly, so what is type 1? If I remind you, type 1, I should just not touch this mouse. So sorry, I am trying a new computer. That's why you are seeing all these difficulties. So type 1 is when the Lagrangian is increasing over time. So therefore, you have a barrier that increases over time, in which case you get supercooled freezing problem. Whereas if I have Lagrangian that decreases in time, then you have the picture in the bottom, and you have a melting problem. Again, both of these problem has a weight nu in front of the right-hand side terms. Okay, and I explained to you before why the sign in front of the nu makes a huge difference in terms of the regularity analysis, also stability. Okay, so we started from the optimal Skorokhod problem, and then we arrived at Stefan problem. All right. So all this is formal. So the question is, can you do it better? Can you do it in a rigorous way? And that is the first thing we did. Okay. So in 1D, this was known, but we prove it. And also in the paper with Gusap, Kim, and Palmer, it was heuristically presented in the multi-D case, but we prove it rigorously that actually, if you solve the optimal Skorokhod problem for mu and nu, and you get this active mass, you get this active Brownian motion distribution eta, then eta solves the unstable Stefan problem for type 1 and stable Stefan problem for 2. So that's great, right? I mean, this is something, at least for me, it's new. Because you just solve one optimization problem to get the whole evolution out of it. Which for me, I mean, so far for me, the way to think about variational approach to evolution problems was gradient flows. This is different. You just solve one optimization problem and you get the whole evolution. So that's great. Okay. Yeah, I just wanted to say that what is actually difficult in proving such a theorem, of course, the barrier is not regular. So the barrier function or the barrier S, it doesn't have nice boundaries. So you need to show, for instance, the stopped measure is concentrated on the boundary of the barrier. I mean, it's not a boundary, right? So it's just, you don't know if the barrier is closed, for instance. So you need to argue and show something like this. And B, eta is positive everywhere in the complement of the barrier. It's also not so clear if barrier is just measurable, right? It can be very porous. In that case, in the complement, it's not clear if the Brownian particle can travel to everywhere in the complement. So you need to show NB, and then you can kind of follow the heuristic reasoning to obtain the Stefan problem. Okay, so that's the difficulty. And also you can do the reverse characterization. So if you have a weak solution of the Stefan problem with weight nu, with initial data mu, then you are going to have a picture that's like above. So I drew the picture there. So it's a solution of a free boundary problem. So you have a free boundary there, right? Now from there, you can recover the optimal stopping time as the heating time to that free boundary. And then, yeah, so they are equivalent. Okay. So that's very nice, except one thing. So we would like to find solutions of the classical Stefan problem. So because that's what we want, that's what's classically modeled after supercooling. And so if you think about what we have proved so far, it amounts to finding nu as a characteristic function. In other words, you want nu to be uniformly 1 in its support. Okay. So for this, so actually it's not so easy for a given mu to see if a characteristic function is, it can be achieved by stopping times. So instead of worrying about that, we decided to, so far we were very successful with optimization, right? So we'll just add another layer of optimization. Okay, so what we will propose is simply adding an extra constraint and now optimize also the target measure nu. Okay, so this you will see in a few slides that it provides us solutions of both Stefan problems. Stable, surprisingly. So we will see. Just a second. 10 minutes, I think. Or do I have? Yeah, okay. So for given absolutely continuous, compactly supported mu, we look for, yes, optimal nu. So the new thing is what? Here in the minimization problem, that I also free nu, but with the constraint that I put in blue, that nu is under a given function f. Okay. So yeah. So of course, when you do not give any constraint, it's best to just stay as mu, right? I mean, why would you move at all to generate cost? Cost is positive. So, but for instance, right, when I have mu like that, that's pictured in the bottom of the slide, and when I put f equals 1, then you will have to move, right? Okay, so that's the problem. So yeah, so that is the problem, right? So you are not only optimizing the stopping time, but you are also optimizing the target. So theorem, when you do this, actually you get characteristic function. That's the theorem. Unless you instantly decide to stop. So if you look at the picture in the bottom, you have your initial measure mu, and some of them, especially if you're small, and if f is really just constant 1, they may just decide not to move, but some of them has to move, right? And even if the mass is less than 1, you may have to scoot over to make room for the portion of mu which is above 1. So this is a non-trivial problem, but you can show that it's either characteristic function or you instantly stop. Okay. So now here is the consequences. It's a well-posed theorem. Okay. So we are setting f equals 1. And to prevent instant freezing, we forced the initial data to be bigger than 1, so that nothing freezes instantly. So that we get an evolution for the entire initial data. Then what you are getting is that the optimal target measure nu is a characteristic function, and the corresponding active mass distribution eta solves the supercooled Stefan problem. Okay, with initial data mu. Moreover, what's interesting is that this eta we obtain is the unique weak solution of the supercooled problem that vanishes in finite time. So as I explained, there is a high generic natured non-uniqueness for this problem. It's a very unstable problem, but with this additional feature of vanishing in finite time, you have a unique solution that's given by the optimization problem. And B, so so you do not, you cannot just start from the initial support. You know, your boundary will have to widen up at initial time and then shrink to give room for this extra mass that's bigger than 1. And so there is another characterization that needs to be made. That's the initial trace. So the initial trace of the active region is given by this obstacle problem. That's okay. So this is the theorem we can obtain for f equals 1. And some of you may be unhappy, but you know, this is restrictive because I can only deal with initial data from a PDE point of view that's bigger than 1 in its support. All right. So we can do this for general initial data. So for general initial data, what I'm doing is that I'm just imposing f to be characteristic function in the complement of the support of mu. So I do not let it freeze in the support of mu, but I let it freeze with density less than 1 outside of the support of mu. Then I get another solution. I still get a characteristic function. I still get a characteristic function nu, but it evolves differently, right? Again, it spreads out at initial time and it starts freezing, but it never freezes in the support of mu, which is k, because you're not allowed to, right? Your constraint f is 0 in k. So what you see as the free boundary is this blue line I draw. It narrows, you know, so it asymptotically approaches the support of mu, but that's it, right? It does not enter k. So, and then with this constraint, you can show again that it's the unique such solution. And again, you can solve where it starts at t equals 0 as an obstacle problem. Okay, so I think that's, yeah, it leaves me just a few minutes and I probably, yeah, maybe, so I get this, you know, I showed you how to, using this optimization problem, I can obtain existence and uniqueness of this kind of unstable problem, which was quite surprising. But it also turns out that what we obtain through this optimization process has stability. But maybe, yeah, okay. So for instance, if I start with 2 ordered initial data or initial probability measure mu1 and mu2, that's, well, not probability measure because you cannot, it doesn't have to be probability measure, by the way, it just is enough that mu and nu has the same mass. So if you start with 2 initial measures that's ordered and you impose the same constraint f, that's not written here, you impose the same constraint f. Oh, here you go, so nu 1, so here f is equal to 1. Then the resulting optimal target measure is also ordered. Okay, so let me point out that Stefan problem, the supercooling one, does not have comparison. And so we are looking at special type of solutions of the Stefan problem that has stability, in particular ordering property. So maybe I should just end with one more thing. So this is the central property, and based on this, you can prove a few things which I do not probably have time. But one of the consequences is that optimal target nu is universal. Again, f is the same. But with common f, it doesn't matter what cost you give. Okay, what's even more remarkable is that it doesn't matter whether you give type 1 cost or type 2 cost. So whatever Lagrangian you have, as long as it's monotone, strictly monotone, increasing or decreasing, you get the optimal target measure the same. Okay, so this is very surprising. I mean, we did not expect it, but such universality holds. And in fact, using this, we characterized our initial traces for our solutions because, right, so if the optimal, let me just say one more thing, maybe then I'll just be done, right? So if you go back and think about these two pictures, you are getting the same target measure at the end for both types of the picture, right? And remember, for the target measure, right, for the picture on the right, it gives you, so the target measure has to do with the initial support of this barrier S, which will correspond to the initial trace of the active region. Whereas on the picture left, the target measure is supported on the the asymptotic shape of this space-time barrier S as time goes to infinity. So it has to do with the optimal target there in terms of the picture right has to do with the asymptotic behavior of the free boundary, which is much easier to figure out. So that's how you figure out the initial trace for the supercooling Stefan using this universality. Okay, so maybe I'll finish here. Thank you.
Thank you, Inwon. Any questions or comments?
Hi, I have an extremely naive question. Maybe it doesn't make sense. So does solving a Stefan problem give, is it possible to give any numerical algorithm to do sampling? For example, if you have a target measure, you start with something very nice, and then you solve numerically solve that Stefan problem. You solve the boundary, the set S and the fair function S and T, and then you run some particles, and in the end you stop at these particles, and then it'll give you the target measure. Or does it make sense, or what are the limitations?
Do you think, so can you repeat this? Because, okay, obviously I don't know very much about sampling, but maybe the audience can give some answer. Could you repeat your question?
Oh, I'm just asking if
yeah.
The idea of solving the Stefan problem will give us some numerical insight on solving the Skorokhod problem.
Yeah, okay. That's a very good question. I mean, so far, the way we solved it, right, is to use Skorokhod problem to solve Stefan problem, right? So if you are, you're asking whether the reverse direction would give you some insight. That's, yeah, I mean, I'm not sure, but, as I explained that the studying purely with PDE tools, the Stefan problem, especially the supercooling Stefan problem, right, is quite it's not giving us much. On the other hand, maybe the melting Stefan problem, right? The melting Stefan problem, which is the picture on the right-hand side, it's very well studied using PDE tools, right? So maybe that would, and there's a lot of advances made on that problem, as Alessio will explain in the next talk. So it's, yes, that may help understanding the Skorokhod problem.
All right, thank you so much.
Mm-hmm.
Okay, try to keep us on schedule. So let's thank.
Okay. Let me stop this.
Yeah, thank you.
Mhm.